Assalamualaikum. We are from Group A, want to present about computational fluid mechanics. This is our group member, consists of 4 members. Our group leader is Anik Lukman. He will present about tutorial for the setup and result stats on CFD. My name is Iqbal Hisham. We present about introduction, theory and objective. Fakrul Ismah present about tutorial on producing geometry and generating mesh. Last, Tengku Imran will present about the result of the theory and discuss the effects of different airflow velocity. So, CFD is a branch of engineering that uses computers to study and simulate how fluids like air, water, or gas move and interact with surface. It can generate a model creation, mathematical equation, simulation, and result. In simple terms, CFD is like a virtual wind tunnel or water tank that helps engineers and scientists test and improve design without needing physical experiment. The CFD software can be used to generate the velocity profile and the y distance versus velocity u graph, which can be used further to find the boundary layer thickness. This is one of the equation or theory that the CFD software used to calculate the properties during the simulation, which is Navier-Stokes theorem. Blassius equation is also one of the equations that are used in this software for the calculation of some properties. This equation is used to calculate properties like boundary layer thickness, drag force on the surface, and the velocity change across the boundary layer. We have 3 objectives, which is first to get a result whether it can relate to theory or not. Second, find the boundary layer thickness from the generated graph. And third, compare the generated velocity profile with theoretical velocity profile of a laminar flow over a flat plate. Next, my friend Isma will proceed with tutorial on how to use CFD software.
Assalamualaikum. My name is Ahmad Fakri Ismail bin Hassan. I will talk about geometry and the dimension. First of all, we need to open Fluid Flow Fluent. Right click to the geometry and choose the new design modular geometry. We're going to draw a rectangle, so start sketching. First, we need to change the grid. Showing 2D, snap, major spacing 0.5, minor step 10. Alright, then we change plane to Z plane. Okay, then we draw the rectangle from the origin. After that, we assign the horizontal and the vertical. Then we give it the geometry. For the horizontal, in my case, is 0.5. For the vertical is 1. Okay, here's our rectangle. After that, we go to the concept and assign a surface to the drawing. Then we generate. Okay, after that, we save the file. We save. We wait for a save. Okay, after that, we go to the mesh. Double click the mesh. Alright. Wait for the object that we draw just now. Okay, we change to the Z plane first for easier as to apply the mesh. We insert the face meshing, face, apply. After that, insert again, sizing for the top and bottom. Choose the edge, top and bottom, apply. For this, we change the element size to the number division, and also the number of division is 60. In my case, it's 60. And then we change the capture curvature, change to no, and change the behavior to hard. Right. Again, we insert the sizing for the left one. As usual, element size change to the number of division. In my case, it's 50 for the left side and the right side. Capture curvature, no. Soft, change to hard. Bias, yes, we have bias, the top one. And bias factor is 70. Okay. For the last one, we insert the sizing again for the right side. Okay, then as usual, element size, we change the number of division. Number of division is 50. Capture curvature, no. Behavior, change to hard. Bias, 70. Bias factor. And for the right side, we need to apply reverse bias. Alright. Then we generate it. Here is the match that we do just now. Okay, now I'm going to name the system. The system we call airflow. The left one is inlet. The right side is outlet. The base is plate. The top is for field pressure. Alright, that's all from me. After this, my teammate Anik will continue this F4 system.
Okay, after we are done with our meshing, we can go ahead, go to file, and then save our project. And then we can go ahead, close this page. Next, you can see there will be a lightning symbol right here. Right click on it and then click on update. And when the lightning symbol turn into a check mark, you can go ahead and click on setup. Here, click on double precision and change the solver processes to 4 and then click on start. After our plate has been generated, we can go ahead and click on check to check for any error. If there is no, go to model and then change the viscose to Lamina. Then hit OK. Next, go to material and air. And it will show the density of the air that we use and the viscosity of the air that we use. Go ahead and hit close. Next, go to boundary condition and inlet. Click on inlet, double click on inlet. And then this is where we will change our inlet air velocity. We will use 1 and 1.5 meter per second, but in this tutorial, I will only show how to use 1. Later, you can go ahead and change this to 1.5. And I will show both of the result at the end. And hit close. For far field pressure, click on it and change the type to symmetry. Apply and close. Next, go to method and change the scheme from couple to simple. And then go to monitor, residual. Change 110 to the power of negative 3 to 1 times 10 to the power of negative 6. I think 3 zeros. So all of them. Hit OK. Next, go to initialization. Change from hybrid initialization to standard initialization. Compute from inlet. And then go ahead and hit initialize. Next, go to run calculation. Change the number of iteration from 0 since it is unreasonable, and then change to 1 million. And click on calculate. It will perform a calculation and it will provide us with the graph of iteration on the x-axis and residual that the software solved on the y-axis. As we can see, this is our graph. After we're done with our graph, we can go ahead and close this page. Next, we can go ahead and double click on result. And here, first you will need to click on the Z axis to change the view to X and Y plane. Next, go ahead and click on contour right here, click on OK, and then here change the location to symmetry 2 on the plane. You can go ahead and hit apply. This is 11 color used. You can change it to 50 for more precise coloring gradient. Apply, and then as you can see, there will be more color gradient. We can change the pressure contour to velocity contour. As we can see, hit apply. Then here is our velocity profile. Next, go to insert and then location line. Hit OK, and then we will create a line from this edge to this edge, which is the position of this edge is x equal to 0.5 and y is 0. The second point right here is 0.5 and y is 1. Sample, we will use 100 sample for this run because it will be more accurate and more precise of next later on during the graph projection. Next, go to chart right here and then hit OK. The data series, click on the data series and then change the location to line 1 that we just created. Go to X axis, change the chart count to velocity U, and the Y axis change it to Y, and then hit apply. As we can see, this is our boundary layer thickness graph, which is the Y or the distance versus the velocity U graph that the software projected. That's all for me, thank you.
So next, for the relation between result and theory, we use boundary relatedness to compare between both of the result. As we can see here, first we need to calculate the theoretical of boundary relatedness. That is for 1 meter per second is 13.3 millimeter and 1.5 meter per second is 10.8 millimeter. Then, we can calculate the boundary relatedness from the result of the CFD. There is a slight difference appears between the theoretical and result from the CFD. The slight difference arises because of CFD results account for complexities and numerical approximations not considered in theoretical solutions. For example, simplifications in theoretical models, theoretical solutions such as those derived from the Blassius equation or other boundary layer approximations rely on assumptions like steady, incompressible, and laminar flow over a flat plate with no external disturbance. Also, here is shown both of the velocity profile for 1 and 1.5 meter per second. For the slide of dark blue color at the bottom of the flat plate for both diagrams, the blue colors means that there is no velocity, while the dark orange means that it has a high velocity. When we use the velocity u with 1 meter per second, the orange color appears at the velocity profile. Also, when the velocity 1.5 meter per second is used, more or darker orange color appears, means that it has more velocity compared to 1 meter per second velocity profile. Also, higher velocity profile is more spread out on the plate on 1.5 meter per second compared to 1 meter per second. When at higher free stream velocities, that is 1.5 meter per second, the fluid carries more momentum. This increased momentum leads to a steeper velocity gradient near the surface and results in a thinner boundary layer. Next, for 1 meter per second, that is red line, the velocity profile is more gradual, showing a thicker boundary layer as the fluid accelerates more slowly, while for 1 meter per second, blue line, the velocity profile rises sharply, indicating that the flow velocity reached the free stream value much closer to the surface. This shows a steeper velocity gradient in a thinner boundary layer. That's all from me.